Uh, Okay, so we wanted to talk about two things: direct product and direct sum and semi-direct sum of Lie algebras. And the reason why I keep on confusing that with the other term is because direct product and semi-direct product of groups, Lie groups in particular, have a very important role to play in this. And actually, uh, well, if a Lie group is a direct product of two Lie groups, then the corresponding Lie algebra is a direct sum of the individual Lie algebras. Similarly, if a Lie group happens to be a semi-direct product of two individual Lie groups, then the Lie algebra corresponding to that Lie group is the semi-direct sum of the two individual Lie algebras. So if we're using the Lie group Lie algebra correspondence in a big way, we could start with the definition of a direct product and semi-direct product of the Lie group, which, by the way, was part of the essential viewing at the beginning of the course. And then from there, gone on to derive what features direct and semi-direct sums of Lie algebras would have. But since we are not really taking that approach right now, we are thinking of Lie algebras as independent identities. Let's try to define the direct and semi-direct sum of Lie algebras directly, using the fact that, after all, these are ways of combining two Lie algebras to form a bigger Lie algebra, two distinct ways, of course. And after all, what you really need to ensure is that the resulting structure is a Lie algebra. That is, it's a vector space, it has a Lie bracket, and the Lie bracket satisfies all the conditions that we need. So let's start with a simpler one, the semi-direct sum. Let's talk of semi-direct sum. Sorry, that's not the simpler one at all. The simpler one is the direct sum, as the name sort of implies, of two Lie algebras. And for the time being, let's deviate from the notation that we have been using so far. Let's use the standard notation that Lie algebras are usually denoted by small letters. So here we are going to call them G and H. These are my two Lie algebras which are going to be combined to form the direct sum of G plus H Lie algebra. Okay? And for the time being, what I'm going to use is that the elements of small g and small h, that is Lie algebra elements, the ones between which we can calculate Lie brackets, those are the ones which we are going to call, which we are going to denote by capital letters. Okay? So this is actually quite standard in the mathematics fraternity. Their group elements are denoted by not group elements, but group labels are denoted by capital letters. So you call it group capital G or capital H, for example. And the elements of the group you use small letters for, and you turn it around for algebras. For the algebra, you typically use small letters for the name of the algebra and capital letters for the elements. This is not universal, it's just one thing that we sometimes use as a convention. And at least when we are going to talk about direct and semi-direct sums, let's use that convention because it's sort of going to keep us clear about what we are talking about. So these small letter things are Lie algebras in their own right. We want to form the direct sum Lie algebra. And of course, first of all, we need to talk about the vector space which the direct sum Lie algebras lives on. And there are no prizes for guessing what that is. The underlying vector space is the direct sum space, some vector space. Does it? Okay, now the important question is, do people remember what a direct sum of two vector spaces is? Yes or no? If you do, we can of course skip a lot of that detail and jump directly to how this works.
Yes, sir.
Okay, so if you remember that, basically, quickly, the elements of a direct sum space formally are actually ordered pairs. So they're actually elements of the Cartesian product of the underlying sets. So you would have elements like this, where capital G belongs to small g and capital H belongs to small h. Remember, once again, you're using capital letters for the elements. So this is a typical element of the direct sum vector space. And in order to form a vector space, of course, you have to define how to add and multiply these by scalars, and that's the obvious thing. That is, GH, when you add that to G prime H prime, this is a vector space addition. Of course, what you do is you do G plus G prime, H plus H prime. And similarly, when you multiply the pair GH by C, you get CG, CH. So this is the obvious part. And what makes the direct sum of two Lie algebras so easy to understand is that basically the only additional thing that you need to specify, of course, is how to define a Lie bracket between pairs. And there also the rule is absolutely simple. You take the Lie bracket of the element GH with the element G prime H prime. Just hold on. Okay, sorry about that. Let's talk about the Lie bracket. Now, what would the obvious choice of a Lie bracket here be? Simple.
Lie bracket of GG prime and HS prime.
Yeah, so the first element will be the Lie bracket of GG prime, and the second element will be the Lie bracket of HH prime. That's the most obvious choice. Of course, this still is not done, because what you need to do is convince yourselves that this is a valid Lie bracket. Firstly, this is a valid product, that it is linear in the elements GH. So if you replace the first element of the bracket by a linear combination, it will work out. If you replace the second element by linear combination, it will work out, and the result is linear in both cases. Okay, that's one part. Then, of course, the more important things, you have to check whether it satisfies the other properties which makes it a Lie bracket. One, that is anti-commuting, and two, that it obeys the Jacobi identity. Now, each of these properties are very, very easy to prove in this case, simply because the brackets here, the brackets in small g and small h are genuine brackets. They have the anti-symmetry and this genuine Jacobi identity property. And using them, you can easily show that this is a genuine Lie bracket. So you have a genuine Lie algebra. Okay. Does anybody need any further explanations for this? Because this is really rather trivial. So you should be able to just work it out by thinking about it. In fact, you can write the whole thing out and see trivially that it's going to satisfy a Jacobi identity, provided, of course, the individual brackets in capital G and small h satisfy the Jacobi identity. Okay, so this Lie algebra structure is really rather simple. And in fact, if you remember the direct product structure of groups, there are also basically the elements of the direct product group are ordered pairs, one from each group, and there the product is of the two elements of two such pairs is simply you multiply them pairwise. So things are really rather simple. And while that is true, there are some details which we still need to sort of keep in mind. And one of the details is very simple. In fact, both of these details, in this case, is very simple. If you take this set, that is, you take elements from small g, pair it with 0 of small h, actually, the null vector of small h, then it's easy to see that this is a Lie algebra, subalgebra. That is, it's a sub-vector space. That's rather trivial to see. It's also a Lie algebra in its own right. That's again trivial to see, and in fact, it's obvious that this thing is going to be isomorphic to G, right? And small h is going to be isomorphic to this other obvious subalgebra you have, which is 0 of small g paired with elements. So this is, of course, if I want to write it in full, this is capital G 0h with capital G belonging to small g. Similarly, this is 0g comma h with capital H belonging to small h. So while this is not exactly the same set as the set underlying small h, after all, these are pairs of elements and small h only has individual elements, it's obvious that there is a one-to-one linear algebra as well as bracket preserving relationship between them. So these are obvious subalgebras, right? And what's also very important is this. Small g is an ideal, in the small g and small h, both of them. So let's drop the ism, are both ideals of G semi-direct, C direct sum H. Right? Now, how do you check that? How do you check that they are ideals? Well, let me show.
Consider
Consider
Lie brackets.
Right. Just check the Lie brackets. Take any take an arbitrary element from small g. Let's say I want to show small g is an ideal. What do I need to do is take this pair, this element from this effectively small g, that is this set, and then take the Lie bracket of this with any element of G direct sum H. So not just a small g element, not an element like this, but any element. And of course, by the definition of how you take brackets, it simply ends up being the pair G comma G prime, this bracket, and the Lie bracket of 0, H and H prime, which of course is 0, H, which means that when you take this Lie bracket, you get an element in small g. And not only that, you get an element in small g where capital G Lie brackets happen as it is, and the capital H part gives you 0. Small h part gives you 0. So this is the null vector. This is basically an element of small g again. And this shows that small g is an ideal. You take the Lie bracket of small g with any element of the direct sum group, direct sum algebra, you are going to get an element in small g. And of course, a very similar argument also occurs for small h. So small g and small h are actually both ideals of this. And in fact, there's another important thing. If you take the intersection of small g and small h, now, what does the intersection, when I say you take the intersection of small g and small h, I don't mean take the intersection of the original Lie algebras because they may have no elements in common. But you really are talking about intersections of these two, which of course has only one element in them, which is 0g, 0h. And this is, of course, the null vector or the identity element for the addition of this direct sum group. Direct sum algebra, sorry. So here what you have is two Lie algebras such that they don't have any intersection other than the null vector of the overall Lie algebra, G sum H, and they're both ideals of it. This is an important property that you have to remember about direct sums. In a direct sum, both the entities which are direct sum happen to be ideals of the sum, and their intersection is just the null vector. Okay, I will not say anything much more about direct sums because the basic properties of direct sums are very easy to derive using all the standard properties of Lie algebras and so on. And most of them are sort of obvious. Essentially, in a direct sum, both algebras do things on their own. Now, the semi-direct sum, that's a slightly different story, but it's more complicated, of course, than the direct sum. And it might seem like we could have perhaps given it a miss, but we can't, because many of the very important Lie algebras happen to be semi-direct sums. Also, the general theory that I was talking about before, the theory about being able to build up every Lie algebra using solvable Lie algebras and semi-simple Lie algebras, there, a very important result is every semi-simple Lie algebra is a semi-direct sum of, okay, so when I say semi-direct, direct is also included in that, of simple algebras. So this whole idea that once you know simple algebras, you know most of all possible Lie algebras, and essentially you know all possible Lie algebras that you will need in physics. That hinges on the semi-direct sum. And even more directly, as far as physics applications are concerned, as I said, there are many important Lie groups which are semi-direct groups, and their corresponding Lie algebras are actually semi-direct sum Lie algebras. Can you give us any example of a semi-direct group in physics which is important in physics?
Lorentz group.
The Lorentz is not a semi-direct group. Lorentz is a group, but semi-direct product of two. The Poincare is a semi-direct product of Lorentz and translations. That's one example which I'm pretty sure all of you know. Another example which you should know, especially from your crystallography classes, essentially for the same kind of reason why the Poincare is a semi-direct product, is that space groups are actually semi-direct products of translation groups and point groups. Essentially the same kind of reason. In fact, why is the Poincare group a semi-direct product of the Lorentz and the translation? Basically, a Poincare group element, of course, is a pair of elements, a Lorentz transformation and a translation. But when you have a Poincare group element like this, a Lorentz group and a translation, and you compose it with another Poincare group element like this, the Lorentz group elements sort of do their own thing, they just get multiplied. The translation that you get is not T plus T prime, which is a translation, which remember is a composition rule in the translation group itself. What you get is lambda gets to act on T prime, and that gets added to T. So basically, before you carry out the combination rule of the second pair, what you are doing is you are actually applying this operation on this translation. So you must have some way in which one of the groups act on the other group elements, so produces a new second group element, and compose that with this group element. So the composition is not T plus T prime, it's lambda T prime plus T. And that makes it a semi-direct product. And correspondingly, the Poincare algebra, which is basically composed of the angular momentum generators and the boost generators for the Lorentz group, and the momentum operators as generators for the translation group, they form a semi-direct Lie algebra. So that structure is very, very important. Now, once again, if we were talking in terms of from Lie groups to Lie algebras, we could have started from this basic fact that in a semi-direct product of two Lie groups, you must have one Lie group somehow acting on another, or rather, what you should have is one of the Lie groups should be homomorphic to, and the set of automorphisms of the other Lie group. And before you combine elements in the second Lie group, you first act upon them by the corresponding element in the first Lie group and then do the combination. And then what you could do is start from that and derive what semi-direct sum of two Lie algebras would be like. But we are not going to do that, as we have said. Whether it would have been easier to do that or not is debatable, but it might even be easier to derive the properties, especially the Lie bracket in a semi-direct sum, from the properties of the semi-direct product of Lie groups. But let's not go there. Let's try to see what kind of generalization of the direct sum can we do. Okay, so basic idea is you are going to form G direct sum, semi-direct sum H. So I put a S here to show there is a semi-direct sum. Once again, the elements will be this, where capital G belongs to small g, capital H belongs to small h. The underlying vector space of for G semi-direct sum H is the direct sum space. So there's no difference there. You already have these as the elements, same as in the direct sum case. And the vector space structure is also the same. Essentially, exactly the same way of addition and multiplication by scalars. What is different is in the direction of, is in this definition of how to calculate GH bracket, GH bracket with G prime H prime. So this is a different rule. So how do we do that? Now, what I'm going to do is I'm going to propose a definition and then try to check whether it works or what kind of properties you would need. Now, just remember, just like you were saying that in semi-direct product of groups, one of the groups does its own thing, and the other one essentially is affected by the previous group before combination. Taking kind of a clue from that, what we will propose is, to begin with, let's propose something like this. Let's say there is a map psi which takes you from the Lie algebra small g, capital G, etc., are elements of that, and it takes it to linear operations on. Remember, a Lie algebra is a vector space. So when you talk of operations that you can do, action of the Lie algebra small g on the Lie algebra small h, you must realize that what we are actually talking about is small g is homomorphic to another set of operations, which operations act on small h, and these operations should be linear operations. So small g, so we are really looking at this. Clear? For every element in small g, we should be able to find some linear transformation which acts on small h, which is going to affect the small h element. Okay? And this should be a homomorphism. Any doubts about that? Any questions about this so far? So we start by assuming that psi is a means by which small g can act on small h. That is, every element of small g corresponds to a linear operation which acts on small h elements. Okay, so this, which means psi capital G will take capital H as an argument and produce an element in small h. This is an element in small h, of course, and capital G is an element of small g. Corresponding to every capital G element, there is a psi capital G, which I could have written that as psi bracket capital G to show that the action of this effect of this homomorphism acting upon capital G, but then it would become rather messy in the notation. You will say psi capital G, which is a linear operator, that acts on capital H, so psi bracket G bracket H. To avoid that, I'm just putting that as a suffix. Okay? Now, with this in hand, some kind of this homomorphism between G and lineage, we will propose a definition for the semi-direct products Lie bracket. And we will see whether this works, at least, or whether we need to put in some additional constraints on the kind of map psi is, etc. Clear so far? Yes?
Yes, sir.
Okay, so this is much straightforward. What we will do is we will think of G as a thing which sort of does its own thing, as we said. So it changes nothing. So, sorry, of course, this is stupid. This is the Lie bracket that we are trying to figure out. That has to be an element of small g direct sum H. So has to be a pair. And the first part of the pair, just like in the direct sum, is G is commutative with G prime, nothing else. Okay? Now, what about the bracket in small h? Basically, in a direct sum, you would have had just this. Now, this is something we are going to modify in a semi-direct sum. How are we going to modify it? We are going to say that in addition to this bracket, what you should also have are additional pieces due to psi g acting on h. So here, now how many possible actions of g elements and h elements can be here? Yes? How many g elements you have? 2. How many h elements you have? Again, 2 in this particular D bracket. So how many actions are possible for g elements on h elements?
4.
4, right?
Yes.
And let's try all of them. Let's put in, to begin with, let's put in everything. So you're going to have alpha acting on psi g h prime plus alpha prime acting on psi g prime h. Okay, this is not done in any book for the simple reason that books either derive this form directly from the semi-direct product of Lie group's result, or they just state the final result and then you ask you to verify. Here we are doing it the other way around. We are just assuming that there is some psi g for every g which will act on h elements, and we are seeing how we can modify our Lie bracket here in the second term. So this is the most general possible thing that I could do. Start, keep the Lie bracket as it is, that is in the semi-direct sum, and add to it contributions like each of the g elements acting via the psi on the corresponding h elements. Clear so far?
Yes, sir.
Okay, in what follows, we are not really going to worry too much about this because this is going to work anyway. So let's not really bother too much about this. But this part, it's not obvious at all that just by putting in some additional pieces, you are going to get a valid Lie algebra. That is, this overall bracket is going to be a valid Lie bracket. In fact, it's not going to be. There will be some obvious things that you can put in immediately. For example, in a general Lie bracket, you must have this. Right? Now, interchanging this and this, the elements whose Lie brackets I'm forming, essentially means interchanging G and G prime and H and H prime, separate. You interchange G with G prime, H with H prime. And you want a minus sign there. Of course, when you interchange G with G prime, the minus sign on this side is straightforward. Here, this term, of course, gets a minus sign. Now, what kind of condition do you think will be there between these constants alpha, alpha prime, beta, beta prime that I've written? You want to be able to interchange G and G prime as well as H and H prime at the same time, right? And get a minus sign. For that, what condition would you put on the parameters alpha, alpha prime, beta, beta prime?
Alpha must be equals to alpha prime and beta must be equal to beta prime.
Are you
And to
sure?
get
You are moving in the right direction, but you're not exactly right.
and there should be a negative between them. Negative sign.
You mean alpha prime should be minus alpha, right?
Right.
And beta prime should be minus beta. It should be obvious that if you do that, then this anti-commuting property of a bracket is going to be preserved. Any questions about this from anyone else? Is this clear? So we can replace this with minus alpha minus beta. Okay, good. Hope everybody agrees that this is the obvious thing. This is the correct thing to do. If you do this, only then we look at a bracket which is anti-commutative. But anti-commutativity is not the only property of a bracket. You need to actually look at other properties as well. Okay, what's the next property that we should look at?
Jacobi.
Well, actually, there's one more, which should have been looked at perhaps even before.
The linear one.
The linear radius, right?
Yeah.
That is, if you replace either GH by a linear combination of two elements, like C1, G1, H1 plus C2, G2, H2, or G prime, H prime by a linear combination of two elements, then the overall result will be linear. Either do this or do that, you will get a linear combination of the corresponding results. That's actually a property which you should check, should have checked even before anti-commutativity, perhaps, because after all, that's a property which ensures that you have a proper product. Okay. Can anybody tell me what will happen if I impose this condition? Remember, when you linearly combine two pairs, each individual term becomes linearly combined. For example, that means if the first term in this bracket gets replaced by this, then you basically are combining C1 G1 with C2 G2 to form the new G, and C1 H1 with C2 H2 to form the new H. Now, can anybody tell me what restrictions, if any, will this impose? For example, what happens to this? This term becomes alpha psi C1 G1 plus C2 G2 H prime, right? We wanted to produce a nice linear combination. That is, I wanted to produce C1 times alpha psi G1 H prime plus C2 times alpha psi G2 H prime. Does that work? Is that going to work? Will it give me what I want? That is C1 times alpha psi G1 H prime plus C2 times alpha psi G2 H prime. Will it? Remember, we already made some statements of what kind of map psi needs to be.
Psi is a homomorphism.
Psi is a homomorphism. It's a Lie algebra homomorphism, right?
Yes.
So, but being a Lie algebra homomorphism means it has to be a Lie vector space homomorphism because it's a vector space in the first place, and it should respect both the vector space linear combination property and the Lie bracket property. We are not talking about the Lie bracket property right now. But you don't need that. What we need right now is basically the fact that this psi has to map C1 G1 plus C2 G2 into C1 psi G1 plus C2 psi G2, the basic linearity property. Homomorphism for a Lie algebra means it has to respect both the vector space structure and the Lie bracket structure. So this part is fine. This term, there will be no problem with. What about this term? Here, G prime stays G prime. You're just replacing one of them, the brackets with a linear combination, remember? So G prime stays G prime, and H gets replaced by C1H1 plus C2H2. But will this give me a linear combination like C1 times alpha psi G prime H1 plus C2 times alpha psi G prime
Yes,
H2?
it will, because this is a linear map.
It will, because we assume that psi
It's a
G,
linear.
after all, the map psi is a map from G to lin H. Then psi G is a linear map. So this also works. What about this term? This will become psi C1 G1 plus C2 G2. And the H will also become C1 H1 plus C2 H2. Right? Will this give me a linear combination with C1, C2 as factors?
We'll have C1 square, C1, C2, and C2 square.
In fact, you will get four terms with
Yes.
C1 square, C2 square, C1, C2, C2, C1. This is not a linear thing. So, and similarly for this, actually. This will not change at all in this case, which is in itself bad, right? Because G prime and H prime has not changed. Or you could have replaced the second factor here by a linear combination. And it would also have, and anyway, beta cannot be there, then this term also cannot be there, right? We have already shown that beta prime is minus beta for antisymmetry. Which means that if this is to be a valid product, in fact, we could have perhaps done this even before looking at anti-commuting. If it's to be valid product, that beta term simply cannot be there. Clear? Okay?
Yes, sir.
Makes sense? Okay, good. So now we have landed up with this result so far. The bracket between GH and G prime H prime. What we are proposing as a valid bracket should be a pair of elements, the GG prime. I'm just modeling this on the direct product of groups, where one of the groups does its own thing, the other one gets modified. So we have HH prime plus psi GH prime minus psi G prime H. Of course, you could immediately update and say, where did the alpha go? All I'm doing is I'm absorbing the alpha in the definition of psi G, right? That's all I'm doing. I'm saying, let's change the definition of psi G. Whatever psi G gave you, alpha times that is going to come out of this new psi G. So absorbing alpha in the factors here, right? So this is the proposal. But is this going to be a valid Lie bracket? Still the question remains, because there's one more very important property of the Lie bracket we need to check, which is, yes?
Jacobi?
Which is obviously Jacobi. And that turns out to be pretty non-trivial. So let's look at that. G1, H1, G2, H2. Now I'm not using GG prime because too many primes spoil the whole thing. So I was tempted to say broth, but anyway. So 1, 2, 3. And that would be easier to also do cyclic permutations on. And here, the first term is sort of easy to see, will be G1, G2's bracket, bracketed with G3, right? And for the first term, we should really have no special thing to do, right? It's basically going to obey Jacobi identity as of its own. If I were to cyclically permute 1, 2, 3 in these three terms, add them together, I would simply get a cyclic permutation of G1, G2 bracket with G3 bracket. And you add them together, of course, it's 0. That's a standard Jacobi identity property for Lie algebra small h. What about the small h part? In fact, we are going to focus on the small h part. Okay. So let's break this up into pieces. Let's not try. Okay. How about the small h part go? In the small h part, you basically have this as the small h part of this bracket, and you're going to do a bracket with h3. So okay, this is where we have to be a bit careful. So we already had h1 comma h2 plus psi g1 h2 minus psi g2. I could perhaps even write psi 2 for short, but anyway, h1, right? This was the h from this bracket. And you have to combine this with this. So from this definition, it's the h element from the first pair bracketed with the h element from the second pair. So h3. Sorry. Okay? But that's not all. You have to do this. So what will this term become? Psi g. What is the g for this? G for this is g1 bracket g2. And h for this is just h3. H prime is just h3. So what will this be? This will be psi g1 bracket g2 h3. Now what will the other term be? Minus? Tell me.
Psi G3.
Psi g3, but it will act on this whole thing, right?
Yes.
So it's not really very simple. It's not. It's pretty non-trivial, but not very difficult to figure out. Let's just see what happens. Any questions about this? So this is, okay, I don't know, okay, I've not really completed all the brackets. The outer bracket, this whole thing is this this third bracket is a commutator here. This one is this term, and this one is this whole term. And of course, I have to close the pair bracket. So this is the small g element, this is small h element. As I said, I won't need to bother about the small g element. That's going to survive, that's going to vanish when you cyclically permute an add. What happens to this? Now, this is non-trivial, of course. It's a pretty lengthy thing, right? And you're going to cyclically permute 1, 2, 3 and add up. Now, of this, there's one term which is pretty straightforward. The first term is h1, h2, comma h3. We will not bother about that because that we know is going to give you 0 on cyclic sum. Okay? Right? h1, h2 is bracket with h3.
Yes. Yes.
So let's not worry too much about that. What we have is psi g1 h2's bracket with h3. Sorry, bracket. Commutator. Lie bracket, not a commutator bracket necessarily. And I'm going to write 1, 2, 3 with bracket in a round bracket here just to indicate that I'm going to cyclically permute 1, 2, and 3. Minus 1, 2, 3 bracket over psi g2 h1 with h3. Right? That's just this term. So this is done, this is done. You see, it's best to keep track of what we are doing. Now this term will become the 1, 2, 3 permutation of psi g1, psi g2 acting on h3. Right?
Yes.
Because remember, this is a Lie bracket homomorphism as well, psi. Or maybe what I will do, I will write this out a bit more explicitly. One important thing, the original brackets in each of the algebras could be some abstract bracket. But the bracket between psi g1, psi g2 are brackets in a space of linear operators acting on a space. That's actually a commutator, right? Whenever you have a bracket on a set of linear operators, that has to be the commutator. Other brackets might be very abstract. So this is really psi g1, psi g2, h3 minus psi g2, psi g1, h3. So that's that term. Of course, the sum over 1, 2, 3 is here as well. Okay, but that's not all. Then you have these. Again, another permutation. Okay, if I were doing this in a pre-prepared slide, I would perhaps put different colors on all of these terms. Psi G3 acting on psi G1 H2. Okay, plus, that's the last term. Psi G3 and psi G2 H1. Right? So I've written all the terms. Okay, let's do one thing, at least to ensure that we can talk about them easily. Let's number them 1, 2, 3, 4, 5, 6, 7 terms. And somehow this whole sum, the cyclic sum of all of these terms have to vanish. Now, quickly, can you spot something that's going to vanish? Two things, of the 7, something which obviously cancel.
1, 2, and 3, 4.
1 to cancel with 3, 4.
No, 1 with 2 and 3 with 4.
1 with 2, 3 with 4. They don't. 1 doesn't cancel with 2. Because the 3 term that you get is the sum of the, look, psi HH, this order here, psi HH, that's going to stay unchanged. You're going to just permute 1, 2, 3, 2, 3, 1, 3, 1, 2, right? That is, you have psi G1 H2 with H3's bracket, then you have psi G2 H3 with H1's bracket, psi G3 H1 with H2's bracket. That will not cancel with this. These are, here you have 2, 1, 3, not the cyclic order, one anti-cyclic order. And each of these terms here, each of these 3 terms here are different from the 3 terms here. They will not cancel. And 3 and 4, exactly the same thing. Both have the same structure. So that's why you thought maybe they would cancel, but they won't. The G1, G2, H3, this will never give a G1, G2, H3. This will give a G2, G1, H3. That doesn't cancel. Okay. But actually, the cancellation is obvious, but it sort of takes a bit of time to think about. Note, okay, this term, number 3 and number 6, both are psi H, right? So that's number 4. But psi here in number 3 and number 4, the indices 1, 2, 3 are in different order. As far as cyclic permutations are concerned, 1, 2, 3 will never cyclically permute to 2, 1, 3.
Okay, now I got
But 1, 2, 3 will cyclically permute to 3, 1, 2.
2.
Because this cancels with this. Okay? Right? Any other cancellation?
4 with 7. 1, 2, 1,
4 with
7,
7.
3, 2, 1.
Right. They will cancel, and that's it. No other cancellations. But now you have this, so let's get rid of all these terms in between. They're no longer there. And frankly, if all you ever had was a psi is a linear map, then these terms will not cancel together. In order that they cancel, what you would have to want, now remember G1, G2, G3 are arbitrary elements, so are H1, H2, H3. So one thing you could always do is first of all rewrite everything if you want to compare them properly. They're all cyclic sums, right? So what you could do is do something like this. Leave this as it is. So psi G3 is acting on the product. Remember, this is a Lie bracket, but this is a product on the on this Lie algebra. Cyclic sum, of course, equal to 1, 2, 3 cyclic sum. This one, right? This whole thing, if this has to be 0, right? This is our aim. If you have to go with the Jacobi identity. So this is 1, 2, 3 cyclic sum of psi G1 H2 with H3. Okay? Plus, sorry, minus 1, 2, 3 cyclic sum. So this is just the Jacobi identity that I'm writing down. Bracket of psi G2 H1 with H3. Now, I want to make these two sums look as close to each other as possible. So what I will do is put psi G3 in front in both of them. Can you see how I can do that? How can I write this with psi G3 in front? Yes? Remember, this is not this term alone. This is cyclic period sum of all 3 terms. So in fact, when you say cyclic sum of ABC, is the same as the cyclic sum of BCA and the cyclic sum of CAB, right? Instead of using ABC here, you could write BCA or you could write CAB.
Yes.
So it's the same cyclic sum. So bearing that in mind, this is 1, 2, 3. And this is will do 3, 2, 1. Yeah. I'm
3,
getting
1,
this.
2.
Sorry. What was it before?
1, 2,
It was
3.
1, 2, 3. Okay, 3, 1, 2. Right. Exactly right. Right. Just tried doing this and saw that I'm not getting what I wanted. Yeah, 3, 1, 2. That's very good. What about this one? The second term is 2, 1, 3. What should be? What should this be? There's 2, 1, 3, anticyclic order. 3, 1, 3 here. This will be 3, 2, 1.
3,
Right?
3, 2, 1.
Remember, that is why these two terms cancel. Right? Okay. Now, let's explain one thing. This is not only going to be
Yes.
true for the cyclic sum, this is going to be true for the individual pieces as well. Why? What's the obvious argument for that? Remember, G1, G2, G3, H1, H2, H3 are arbitrary elements of small g and small h, respectively. So instead of G1 and G2, I could have taken the identity, that is 0, right? I could have chosen them to do anything. Clear?
Right.
So I could have chosen them to be 0. In which case, psi 0, of course, is 0, so that term will drop off. So the G1, G2 will contribute nothing to the sum, only psi G3 will contribute to the sum. And that happens on both sides, right? As a result, instead of this being valid only for the cyclic sum, it's actually valid for one individual term, maybe the third one, where we're using G3. Or the term which is actually written here. That should be the first term, perhaps, of your cyclic sum. Doesn't matter. You understand what I'm saying, right? You can make the other 2 terms in the cyclic sum simply drop off by choosing those G's to be 0.
Right.
And it works both ways, right? If this works for individual terms, of course, it works for the cyclic sum. So, what this really tells you is, let's say G3 is any element, G, doesn't matter. Bracket with H1, H2. In order that the Jacobi identity be satisfied, you must have this psi G H1, H2 bracket plus what? You want to make it a plus? H1 psi G H2, right? It's just this, except that I've just written one of the terms because other 2 terms I've just been able to make 0 by choosing 0 for the elements. And I've just rewritten the second term here, replacing the minus with a plus by rearranging. But can you realize what I've done here? Why have I written it like this? This should tell you that Shaiji is, if the Jacobi identity is to be obeyed, Shaiji cannot be any map, but a very special kind of linear map, not any linear map. But what is this special kind of linear map called? Hint, this thing is a product, right? So basically it's acting on a product of two elements to give you something like this. So what kind of operation, well-known operation has this property, from which this property derives a standard name?
Derivation.
What? Sorry, I couldn't hear you. What are you saying?
Talking about that derivative, it will no, that is
Right, there's a derivative property. It's like DAB plus ADB. It may be a bit difficult to see because, well, simply because we are writing brackets instead of products. But this is Shaiji acting on the product between H1 and H2, which is what the bracket is here, equals the product of Shaiji acting on H1 times H2, and the product of H1 times Shaiji acting on H2, right? Exactly the derivative property for products. So, what you demand here is, you go back on your demand originally, you don't say this Psi is a homomorphism from G to lineage. You modify that. You say Psi is a homomorphism from G to a subclass of lineage, a very important subclass called the class of derivations on H. These are linear operators which have this particular property. Okay? Operators which have this property. They're called derivations. They are very important. And by the way, if we had started from a Lie group and looked at elements very close to the identity and asked what will that do? If we had started, that is, if we had started from the Lie product or semi-direct product of two Lie groups, and looked at elements close to the identity and asked what would the corresponding algebra be, the derivation, the fact that this map Psi has to be a derivation would have come automatically from that. But here at the end of this calculation, we have seen that in order that the semi-direct product be at all defined properly, that is, be a bracket, here what you have to have is this. This definition works fine. Okay, the definition top here. But with one important catch, this Psi G has to be a derivation. A derivation on H is simply a map which obeys that product property. But Psi has to be a map, a homomorphism from G to del H. And then this works. This is a perfectly good genuine D bracket. So we have been able to combine the two Lie algebras in such a way that their underlying set is the underlying vector space is the direct sum vector space. Underlying set, of course, is the Cartesian product. In one, the Lie bracket is simply each element does a Lie bracket on itself. That is, this term is not there. Of course, you can see that a direct product is a special case of a semi-direct product in a sense. All I have to do is say that the derivation we are using is 0. Psi is, of course, 0 is, of course, a derivation, right? 0 acting on the product, 0 acting on AB will give you 0, which is 0 acting on A times B plus A times 0 acting on B. So if you say that is this Psi, this particular map that we are talking about, which maps G to their H, just maps G to 0 of H, then we are done. G to 0 of H meaning the operator which is the null operator on H, not the element 0 of H. Then this is going to give you the direct product. So direct product is a special case of semi-direct product. Sorry, again, bad choice of word. This will give you the direct sum, which is a special case of the semi-direct sum, which is again an obvious consequence of the fact that the direct product of groups is a special case of semi-direct product of groups, right? Because in that case, what happens? In a semi-direct product, at least for one of the groups, the first group has to act on the second group element and then combine with the other second group element. But this action is via some kind of automorphism which acts on the second group. So if that automorphism happens with the identity, then of course a semi-direct product becomes a direct product. Correspondingly, if psi G turns out to be the null map for all G, that is, psi becomes the null map from G to der H, then the semi-direct algebra, sum of algebras becomes the direct sum of algebras. Okay? Clear? Is that clear? Any questions? Okay, the very important question about this. This is a rather lengthy thing that we did because we sort of tried to justify why the Lie bracket for a semi-direct sum should be the way it is. Usually in textbooks, it's either derived from the semi-direct product of Lie groups, in which case that's a semi-lengthy derivation, but this follows automatically. Or they just state that this is the case. We are trying to construct this out of what are the possible things. So any questions about this construction? Okay, this is something you won't find in most textbooks, I guess. I don't know whether this is in any textbook. But this should be sort of easy enough to understand. Okay. Then there's only one question that remains about semi-direct sums of Lie algebras, which is what is the relationship between G direct sum, semi-direct sum H with the original ones, G and H. In the original case, we have seen that G and H has an intersection which is the null vector of the semi-direct sum. This zero doesn't mean it's a empty set. It means a singleton set with only one element, the zero vector of the direct sum. Now, what about this was for the direct sum, right? What about the semi-direct sum? First of all, what will be corresponding G and H? That is corresponding sub algebras of G direct sum H, which will be isomorphic to small g and small h. That is sort of obvious. That's simply going to be, again, the same thing. 0h, the capital G runs over small g. This is obviously isomorphic to small g. And small h is isomorphic to this 0 small g, capital H. The capital H runs over small h. So these are the two subalgebras of capital G, small g direct sum H, which are actually isomorphic to small g and small h respectively. But we have seen that this is the same as in the case of the direct sum. No changes there. For the semi-direct sum, and this intersection is also null. That also works, right? Clear? So what else do you have? What did we have for the direct sum? For the direct sum case, we saw that small g and small h are both ideals. Because if you took this and did a bracket with g prime h prime, you are going to get an element like this again. Now, is that true here? Are small g and small h both ideals? By the way, are they both subalgebras? The small g, the subalgebra is sort of easy to understand from this bracket. The small h is subalgebra. This one. Is it a subalgebra? Is it closed under, that is, if I take two elements like 0gh and 0gh prime, take their Lie bracket, will you get a term like 0g with some element of h? Can you check that? Of course, according to this rule, this term is obvious. You're going to take 0g with 0g, no problem. Okay? So it's going to be an element like 0g with something from H. This thing is from H is obvious, right? It's from H, no matter what H prime are. This bracket is in H prime is in H, so psi g, which is a derivation acting on H, acting on an H element will give you an H element. This is also an H element. So no problem moving it's a subalgebra, right? It's going to be of the form 0g with some element of H. Question: is this subalgebra isomorphic to small h? That's what I have claimed here. That this is a subalgebra is not a problem. Take any two elements of this kind, form their Lie bracket, you are going to get an element here. But is this going to be the same Lie bracket essentially as that of small h? That is, am I going to get this? If I get this, then corresponding to every small h element, there is corresponding to capital H, which is in small h, there will be a corresponding element 0g h in this pair in the checksum, in the semi-checksum, and then this will work out. That is combining Lie bracketing to capital H elements essentially will be mimicked by Lie bracketing the pairs. But is this true? Quickly, is this true? Is the question clear to everybody? That this is a subalgebra is obvious because if I take the bracket of two elements from here, like this, you are going to get 0g in the first place. Because 0g, Lie bracket is 0g is 0g. And that's all you need to prove that this is subalgebra, right? It's closed under the bracket. But can you show that this is actually isomorphic to H? That is essentially the same Lie algebra. That is, apart from this 0g, whatever you have is just a Lie bracket of H and H prime. Nothing else. What will it be? Bracket of H with H prime plus psi g. What is capital G here? 0g. So what's the answer? What you should get is H prime plus psi 0g H prime minus psi again 0g, because both G and G prime are 0g. Right? So am I still connected? With this much silence, it's difficult for me to figure out. Yes? Am I here?
Yes.
Okay, I could hear some response. Now, remember, psi is a homomorphism, right? And that will immediately tell you the psi 0g has to be the null map. Isn't it? After all, 0g is 0 times any capital G, right? Because 0 is a number. Just use the fact that psi 0g, psi is a linear vector space homomorphism. We don't have to worry about the Lie algebra part. Because it's a linear vector space homomorphism, psi 0g, which is psi 0 times g, is 0 times psi g. The map is a null map which maps every element to 0. Which means this is 0, this is 0. They don't cancel, they're both equal to 0. So you do get H comma H prime. So this is a subalgebra. Right. Now, what else did we figure out for in the case of the direct sum? What was special about small g and small h? They were not just subalgebras, right? They were what?
Ideal.
Okay. Now, which of these two, small g and small h, which of them are ideals? Or are both of them ideals? Or are none of them ideals? So I'm looking at the corresponding result for the semi-direct sum. The direct sum, both the inputs which went into forming the direct sum were ideals of the direct sum. Here, so far we have seen that this part, actually the relationship between GH and the semi-direct sum seems to be very similar. The intersection is the null vector of the direct semi-direct sum space. You do have small g and small h, both of which are isomorphic to sub-algebras of this, or we just don't say isomorphic to sub-algebras of this, we just say G and H are sub-algebras of G direct sum H. So far, everything is very similar. What about the idealness? Is any or all of GH, small g or small h, an ideal of the direct sum? Of course, ideal would mean you have to form a Lie bracket of an element from small g. If small g were an ideal, you have to form a Lie bracket of this with any element from the entire thing, and you should have a small g element. Will that work? It should be pretty easy and quick to
No,
fix.
sir, it would not work because of the psi g prime.
So basically what will happen if you took this Lie bracket, that is capital G0H with G prime H prime, what you will get, in the first place you will get G comma G prime. No problem. But the second term, will you get 0H? Well, 0H with H prime is 0. As you were saying, this term doesn't contribute. Psi G H prime, H prime will be there. That's not necessarily 0. Psi G prime H is 0 because psi G prime is a linear map. It acts on 0, it gives you 0. But you will get this, which means that although small g is a Lie algebra, sub-algebra in itself, it's not an ideal. Small g is not an ideal. What about small h? Is that an ideal? That seems even further from the possibility, right? Because it's small h which behaves in a complicated fashion. But let's check. Let's take G prime H prime and form a Lie bracket with, okay, let's take 0G H and form a Lie bracket with G prime H prime. Of course, 0G Lie bracket with H prime is going, G prime is going to give you 0. Right? And I don't even care what you will get here. What you will get here is something you can figure out. Either you will not get H prime, right? You will get H prime plus what? Minus psi G prime H. Psi G H prime in this case will give you 0 because psi G is psi 0G, but you will get minus psi G prime H. Right? So you will not get H bracket H prime, but you don't want that. All you need to ensure is this: when you take a Lie bracket of 0G H with any element from the semi-direct sum, you are going to get an element in small g. That is, an element with 0G as a first element. So small g is not an ideal. So okay, I said you will get an element of small g a while ago. That of course was wrong. You're taking an element of small h, bracketing it with any element, you're going to get an element of small h. So h is an ideal. So here you have two subalgebras with the null vector as the only common element. One of them is an ideal, the other one isn't. That is the difference between semi-direct sums and direct sums. In direct sums, both objects which go in are actually ideals. Here one of them is, the other one isn't. So quickly, can anybody guess? In the Poker algebra case, you have two subalgebras. One of them is the Lorentz algebra, composed of just angular momentum and boost. The other one is this translation subalgebra. That is just the momentum operators. Which of these subalgebras is an ideal of the Poincaré algebra? In this case, which one takes the form of G? Okay, which among the Lorentz on one hand and the translations on the other? Which ones actually transform like, which are like capital, like small g, which are like small h?
Lorentz is like G and translations is like H.
Right. In the group sense, Lorentz is like the exponential of this Lie algebra G. That is basically it's the thing which only forms products with itself, whereas translations get affected by Lorentz before combining. So in the algebra sense, the Poincaré subalgebra is like H, and that's the ideal. The Lorentz. This may seem a bit counterintuitive if you think about it, because the bracketing in small g is much easier than the bracketing part in small h, right? In this direct sum. In the direct sum, of course, both were identical behaviors. So if one was an ideal, it would be obvious that the other would also be. Here, one is an ideal, the other one is. Okay. And remember, this is, of course, very important physically. The very fact that Poincaré algebra is not a direct sum, but it's a semi-direct sum. And translations are an ideal of that. The algebra has immense physical consequences. But as far as we are concerned, our major concern right now would be that there is a result which I'm definitely not going to prove, which says that any Lie algebra can be a direct sum of a solvable and a semi-direct algebra and a semi-simple algebra, and every semi-simple algebra is a semi-direct sum of a bunch of simple algebra. Once again, let me remind you, solvable algebras cannot be completely classified. At least nobody has been able to do it yet. But semi-simple Lie algebras have been completely classified. And in most of physics, what we will need are semi-simple Lie algebras. So their classification is complete. So next time we will start talking about the complexification, then talk about the scaling form, which is like this is quote-unquote metric tensor that we spent quite a lot of time last day trying to figure out, and then try to show various important results, which will follow from some very basic simple calculation. Okay. So essentially within 2 or 3 classes, we will be able to sort of classify hopefully all the simple Lie algebras and understand what their behavior is like. And generate tools which will allow us to sort of, if we are given some as yet hitherto unstudied semi-simple Lie algebra, which of course doesn't exist, remember, you have a complete classification. But suppose in some physics problem you meet a Lie algebra, semi-simple Lie algebra which you have not handled yet, you would know how to handle that. Okay, any questions before we wrap up? If not, so let's wrap up today. On Wednesday, we will start on complexification. And you will get your next problem sheet, which is completion of this reconstruction of a group from an algebra. And I will ask Gaurav one of these days to sit with you and explain any steps you may have missed in that part. That part is very much part of the syllabus, by the way. Don't think that because I have not lectured on it, I will not ask you that things from that in the exam. Of course, not the whole thing. The whole thing is big. But at least ensure that you have all understood what you're doing in that particular assignment. Okay, bye for now.